think uncommon lower branch solutions in pipe.
Hello everyone, well thanks very much to the organizer. So the work I'm presenting now has mainly been realized while doing this postdoc in Bristol. So we're back to pipe flow. So I will talk about this laminar turbulent boundary in pipe flow and show how you can identify finite amplitude solutions along these edge trajectories. And since we heard size matters, then try to see these ideas that are kind of accepted in small computational domains can be generalized to larger computational domains, and what this implies eventually on the transition scenario. Thank you. So I should acknowledge my very friendly collaborators from Bristol, so Rich Kurzweil, Ashley Willis, who talked earlier this day, and Chris Pringle, who's giving a talk tomorrow. So nothing has changed, as I said. There's still cylindrical pipe flow with a length L and a diameter D. And so we're driving the flow in our pipe by a fixed mass flux, as if you were pulling the flow with a syringe. And so the laminar flow is stable to infinitesimal disturbances, but we know now from experiments and also simulations that at least three-dimensional perturbation can lead to a finite amplitude instability. So for each three-dimensional perturbation, there can be a critical threshold, critical amplitude, and it's interesting to study what the flow is like near criticality if you want to understand transition. So, of course, we will do this numerical study using this numerical code used also by and developed by Ashley Willis, which assumes periodic boundary conditions between the inlet and the outlet. So first we'll begin with short pipes and track these trajectories on the laminar turbulent boundary in the same pipe as used by Schneider and Eckart, so Reynolds being 2875, and the pipe has a length of 5 diameter. And so far we're not imposing any symmetry. So this is the resolution we use, which leads to a dynamical system of the order of 10 to the 5 degrees of freedom. And the initial conditions that we will use for the bisection method are exactly the same as those presented by Professor To just before. So we take a turbulent snapshot U star that we average, say actually, and then we will weight this actual average with the 3D residual. So this 3D residual we will weight it by a constant beta. It's what Professor To just called FAC before. And by playing with this constant beta, we'll try to land on this laminar turbulent boundary. The idea being that for beta equals 0, well, we have a two-dimensional perturbation to the laminar flow, so it will not trigger transition, whereas for beta equal 1, you will be turbulent. So by playing with this constant beta, like here, so here I represent the 3D energy, so the energy of the three-dimensional modes in the flow integrated along the volume as a function of time. So as you can see here, if my beta is too big, then my energy grows until and stays saturates at a turbulent level. So I reduce beta. If beta is too small, then it will quickly relaminarize to 0. So 0 of energy corresponds to the laminar flow. So just by adjusting beta to up to machine precision, then we can generate a trajectory. So this trajectory neither goes laminar, laminar in the sense of the Hagen quasi-laminar flow, nor goes turbulent. So how do I differentiate here between turbulent and laminar turbulent boundary? That's pretty important. It's not based on lifetime here. It's just that we noticed by experience that there are 3 distinct levels of E3D, so 0 here, which corresponds to the laminar state. This order of 0.1 here, which corresponds to the turbulent state. And we notice that some trajectories can stay at a level which is intermediate. And this is by eye how we decide that we are on this basin boundary. So these are edge trajectories, edge of chaos, some people call it, or edge of turbulence, which is also the edge of the laminar state, of course. So interesting is also to look at various fixed points in the pipe domain and look at the velocity signals. So here's the actual velocity signal, and you can see that the signal is generally chaotic, I would say, but on short temporal windows, then you can notice that the flow looks correlated in both time and space. So for example, clearly here at the beginning of this trajectory, a bit here as well, whereas here, for example, I would say that there's absolutely no correlation. So this oscillating pattern that you see here or there looks like the signature of, say, a traveling wave. Red, green, blue corresponds to different points in the pipe. It doesn't matter really where they are. Some are near the boundary, some are in the center of the pipe.
It's the magnitude of the velocity, or is
This is the actual velocity at one given point. That's what you could measure experimentally, for example. Yes. We have the same regardless of the direction of which component we use or where the point is. It is, yes, thank you. So the idea is to say, well, maybe here we are approaching some kind of traveling wave motion, and the flow looks more recurrent. So we need a way to measure these recurrences along the same trajectory. So to do so, well, this is a state space formulation. So if we start a trajectory from at the time ti and integrate forward in time until a time t, possibly shifting, but we will ignoring in space, but we will ignore this possibility here. And then look at when the flow comes back the closest at time t to where it was at time ti. So by taking the minimum of this function, we can find R mean, which corresponds to the closest return from a trajectory starting at time ti. Of course, an exact recurrent solution, like a traveling wave or a periodic orbit, would have R mean equal exactly 0. So here is the function Ri for several starting point t. So you can see that here the flow does not look like it's going back to where it started from, whereas here you see that you're quite close to your initial point, whereas here you're not. So this is a recurrent signal than this. We're all still studying the same trajectory. Now, by linking all these minima, this is my function R mean. So if I do the same calculation for many more points, then this is my R mean signal along still the same edge trajectory. And I can see an alternance of rather relatively low regions for R mean and high regions. So this dips here corresponds, as I can interpret it, to a more recurrent field, and possibly, that's the idea, we're in the neighborhood of states which are R mean equals exactly 0. So to do that, I won't give too many details today about this, but we use a Newton-Krylov algorithm to try to look for states in the neighborhood of these dips A, B, C, D, E, to look for states with exactly R mean equals 0. So for example, these two states A and B along the trajectory look like this, and R mean is of the order 0.1. So by applying this Newton-Krylov algorithm, we managed to converge to states which are rather close to these ones, which are indeed characterized by R mean equal, well, technically 0. And so what are these states? They are traveling waves. They are the same as computed by Pringle and recomputed later by with Viswanath. So a three-dimensional traveling wave with a low speed streak here and rigid high speed streaks over there, and you can see also the cross-stream velocity, so a big vortex. And those two ones are exactly the same traveling wave modulo rotational shift. So this leads us to the idea that this edge trajectory that we were studying is actually going from the neighborhood of one of these traveling waves, then leaves this neighborhood, comes back to the same traveling wave, but modulo shift, leaves, comes back again, and that possibly this laminar turbulent boundary, at least this trajectory, could be structured around this network of traveling waves, and that they would be linked by heteroclinic or relative homoclinic connections. So, imposing symmetries on the flow can help maybe to find new solutions and also simplify the dynamics. So it might look absolutely artificial. We impose a rotational symmetry M0 equal 2 and shorten the pipe as well. So what do we have in this case? This is still 3D energy, so we are again computing a trajectory on the laminar turbulent boundary. And first, the dynamic seems quite chaotic, I would say, and after a while, it looks like the energy is reaching a plateau. And so in this state, this edge trajectory, as for example in Toe's talk or Bruno Eckhart's talk yesterday, the edge trajectory is attracted to a state. And by playing with the initial condition that we take, we can find two of these local attractors on the edge. They both are traveling waves. So this one, for example, was already discovered before, while this one on the right is a new traveling wave, unknown so far. So by playing with the symmetries of the flow and the length of the pipe, we can discover many different traveling waves, each characterized by different symmetries. And so I encourage you to watch Chris Pringle's talk tomorrow. We'll try to classify all these different traveling waves using the symmetries. So a question, sorry for getting backwards, is why do we have here an attractor on the edge, at least a local attractor, and a chaotic motion on the edge in the previous case? Well, the idea is that the answer lies in the number of unstable eigenvalues of these states. So all the states that we have found so far are unstable. But in the case where they have at least one or maybe two unstable, strictly more than one unstable direction, what we notice that the most unstable eigendirection usually points out of this laminar turbulent boundary. So a natural, an unconstrained trajectory could approach it maybe and would be repelled away. Now, by doing this bisection, we actually get rid of this main instability direction, but there are still others. So by constraining the trajectory to be on the laminar turbulent boundary, then even if we go to the neighborhood of such a point, we still repel the way along the unstable manifold. Whereas by imposing symmetries, if we manage to find, if such a state exists, a state with only one unstable eigendirection, then maybe a natural trajectory will approach it and be repelled. But by doing this bisection and killing this instability, then we have a state which constraint for the dynamics constraint to the laminar turbulent boundary becomes now a local attractor. So that's the main difference. So of course this case is interesting if there are such states, so that it allows us to naturally find new solutions. So that's a sketch of what we've found so far. So it's a really simple sketch about the structure of the laminar turbulent boundary as seen by such a transitional critical trajectory. So if here is the laminar flow, here is the turbulence. The simple idea is to say that this laminar turbulent boundary would be a hypersurface in phase space. Now, if you start with an initial condition which is below, well, maybe you will approach one of these states, but since you're below, by definition, you will decay. If you start above, you will go turbulent. Now, if you start exactly on this hypersurface, now the idea is that you will transiently approach saddle points, which are still saddle points on this hypersurface if the number of stable eigenvalues allows for it. And if you find a state with one unstable eigenvalue only, then the edge trajectory will be attracted by this local attractor. So this is a rather simple idea, but of course, how does it apply for maybe longer domains, since we would like maybe to study not only temporal chaos, but maybe closer to something closer to transition to turbulence? Well, you might have seen this plot before today. So in order to tackle this longer system, well, we have to make a trade-off and then use a long, study this 2.5D model presented by Ashley formerly, and with only two modes in the azimuthal direction, so the modes 0 and 3 and also -3. So as you've seen, if we generate edge trajectories, now we have this interesting feature really close to real pipes that we can have localized solution. So first, I will show you the idea that these traveling waves found in the same system in shorter pipes compare quite well to the structure of these so-called edge puffs, at least in this reduced model. But can we apply really the method that we've seen really in the first part of the talk to such domain? So by increasing the Reynolds number, we found that doing this bisection, also with this M0 = 3 symmetry, leads us to the same case as before, where we seem to have a relative attractor on the edge. So the edge trajectory is attracted by a state. So the idea is, what is the state? It's interesting to see that we have to push up to such high values of Reynolds number where the turbulence is, in this reduced model, is obviously contaminating the whole domain. However, the state that we have found here is, well, seemingly a traveling wave, and is localized, so both in the z direction, the actual direction, also quite localized, if we look, this is the actual vorticity, in the radial direction. So if we have a look at the structure of this state, so this here is the actual direction. You can see that, well, indeed, it's really localized on a length which is, well, shorter than a puff, say. You should remember that puffs don't exist at these high values of Reynolds number. So this is here the disturbance kinetic energy. And at 4 cross-section, different cross-section, we will have a look at the cross-section velocity field. You can see that here, it means really where the energy is localized, we have the appearance of a clear critical layer. Okay, so this leads me to, well, almost the end of our talk. So the idea, let's speculate a bit, though we're only using a 2.5D model. Maybe, so that's, it seems like this scenario, at least in this model, still applies. And here is, again, a sketch of this laminar turbulent boundary. And a localized traveling wave seems to sit on it. So of course, if you start just below, maybe you will approach this localized pattern and then relaminarize. And then if you start from above, then you will approach it. And then, well, suddenly the flow will start to expand, and we will have extended turbulence contaminating the whole domain. Therefore, this suggestion of, or this idea that maybe the behavior of a slug that you see in physical space could be explained in terms of dynamical system by, well, simply a trajectory on the unstable manifold of this localized state, or maybe a heteroclinic connection between this point and maybe another state embedded into this extended turbulence regime. Of course, well, these are conclusions, but also some open questions. So it seems that this laminar turbulent boundary is structured around a network of exact solutions which are interconnected through heteroclinic, homoclinic connections. This method that we used here not only allows us to find traveling wave solutions, but it allows us to identify the ones that are really visited by the system. So maybe the most relevant coherent states for transition. The use of symmetry subspaces, though maybe a little artificial, helps us to identify a lot of new solutions and simplifies the dynamics by reducing the instability of the states. And it seems that this method is maybe applicable to tackle this transition in more realistic flow. Thank you very much.
Question?
What do you know about the comparative spatial complexity of the traveling, isolated traveling wave solution that you presented and the PUS?
So the localized one. Can you repeat again, sorry?
Yeah, just comparing the spatial complexity of those two fields. Like the one that you showed has assumption of has just 3 Fourier modes or 2 or 1 Fourier modes in this direction. So it has fine scale structure in the radial and azimuth directions, but not.
Okay, so I'll be careful about comparing a puff solution, even in this reduced model, to this localized traveling wave, because the Reynolds number is so high. And it seems like the flow here in this localized state is dominated by this critical layer which don't really exist in puffs. So the question are, do puffs exist at Reynolds 10,000 but are unstable and then would possess a critical layer? I don't know. But it makes the comparison pretty difficult. But it's true that, I mean, sometimes we call them like puffy traveling waves because they have a length which reminds us of the order of magnitude of a real puff.
And so that was 10,000, our Reynolds number 10,000, and have you brought them down to Reynolds numbers comparable to the
No.
Okay. More question?
So do you observe any changes in the profile of the mean flow along the length of the path?
Yeah.
The profile of the mean flow changes. Is there something similar?
I didn't check that. I guess there must because, well, simply there is a stronger mean cross-sectional flow, like especially in the critical layer again, and this must modify locally the actual mean flow. I didn't check this data.
Okay, so